For question 10, again I've changed the numbers, but the method will be the same as the one that you need to use. So it tells us about the filament. It tells us what the power and the voltage for the lamp are. It tells us the radius of the filament and the temperature it operates at. And it asks us to find the resistance of the filament when it's operating at its normal temperature. But when it's operating at its normal temperature, it's doing its normal job, which is to be a 100 watt, 230 volt bulb. So to find the resistance, we know the voltage, we know the power. We need a formula that links those together. If we look at the data sheet, even though we should probably remember it anyway, it's always reassuring to know that on the data sheet there are formulas for power. P equals VI equals I squared R equals V squared over R. So if those formulas, given that we know power and we know voltage, we're trying to find resistance, then P equals V squared over R looks to be the one that we should use. So we start with the formula as it appears on the data sheet, or as we would have learned it. P equals V squared over R. We're trying to calculate R. So we rearrange the equation. R equals V squared divided by P, which is 230 squared divided by 100 is 529 ohms. You've got different numbers, so you get a different answer. Next part of the question, show that the length of the wire in the filament is 0.20 meters. If you get a question that says show that a particular thing you're going to calculate has a certain value, what it really means, it doesn't mean you should use the value of 0.2 in your calculations to prove that all the numbers work out. It basically means find the length of the wire, and then once you've found it, just check that the answer you get is what you're supposed to have got, 0.2. So you should go about the question in exactly the same way as if it had said find the length of the wire. You don't actually use that answer that's already given. So we now know the resistance of the wire, got to find the length. So that should ring a bell. We should know that we're dealing with resistivity. And if we look at the data sheet gives the formula in the form resistivity equals RA over L. I don't like that form myself. I don't see the use of it. I much prefer the form where you use resistivity to find resistance, but never mind, that's what the data sheet gives. That's what you'd have with you in an exam. So we're trying to find the length. So let's rearrange the formula to find the length. Length equals R times A divided by rho, the resistivity. Now before we can use this formula, we need to calculate A. And we could put the numbers in and put it on our calculator, but that would get quite messy, so I prefer just to do a little side calculation to find the area. So area equals, well, it's pi r squared, and the radius, and note the question doesn't actually tell you the radius, which is a bit artificial, because if you ever measured a wire, what you really measure is the diameter. But the question's made life easy for you, it's giving you the radius, but when you're doing other questions, have a careful check to make sure that it is the radius that's given, not the diameter. So the radius is 92 micrometers, so that's 92 times 10 to the minus 6 meters. So if we work out the value for the area, we get an answer of 2.7 times 10 to the minus 8 meters squared. So now we've got the area, we can continue finding L. So L equals R, which is 529, times A, which is 2.7 times 10 to the minus 8, divided by the resistivity, which is 7.0 times 10 to the minus 5, which gives us an answer of 0.20. The calculator says 0.204, but we're only going to use two significant figures, so 0.20 meters. So we've got the answer. and it's what we're looking for, so that we've shown that that was the correct value. Part B of the question says that near the end of its working life, the radius of the filament has decreased, and also it operates at a lower temperature. And it says at this new temperature, the resistivity of tungsten has gone down. Discuss whether the lamp consumes electrical energy at a rate of 100 watts near the end of its working life. So discuss means sort of find out, state and explain the reason for that. So how are we going to do it? Well, let's check. It says consumes electrical energy at a rate. Now just remember that that means that's what the power is, because it says 100 watts, so it's still got units of watts. So the rate at which it consumes energy is just another way of saying the power. So will the bulb still have a power of 100 watts with these new conditions? And we know what the power depends on. We'll go right back to the start of the question. Power depends on V and R. Well, we know the voltage won't change. Just because our bulbs got old, it's not going to have made the power stations change the voltage they're providing. So what we need to know is, has the resistance changed? Now it doesn't actually ask us to calculate the new power. And sometimes there'll be questions where you could just tell by the numbers whether it would changed or not. Here it's a bit more complicated. I think we are going to have to do a calculation, because the radius has gone down. That means the wire is thinner, and that would cause the resistance to rise. But the resistivity of the tungsten has gone down, so that would cause the resistance to fall. So we've got something causing the resistance to rise and something else causing the resistance to fall. And without doing the calculations, we won't be able to work out which of those things dominates. So we need to work out the new resistance. So the new resistance is rho L divided by A. Forgot to work out the new area. New area pi times, and it's 80 micrometers. Yours of course is a different number. New area 2.0 times 10 to the minus 8 meters squared. So the new resistance, because the bulb is operating at a cooler temperature, it's got a lower resistivity. So the new resistance is 6.4 times 10 to the minus 5. The length of the wire is the same, 0.20 in my case, or 0.25 in your case, divided by the area. So I get a new resistance of 640 ohms. So therefore, I get a new power of V squared over R, 230 squared divided by 640. .83 watts. So I've shown that with the numbers I've got, at the end of its working life, the bulb doesn't consume electrical energy at a rate of 100 watts, it actually consumes it at 83 watts. Which would mean, of course, that the bulb would actually look darker. So since the question did say discuss, perhaps we ought to actually write our conclusion. So we can write, so bulb does not consume electrical energy at rate of 100 watts near end of life. Just to prove that we've really understood what we're trying to do, we've not just done some random calculations.